how we can exploit the memory hierarchy for the maximum possible utilization of the memory. So here, what is included here? You can see these are the subheadings which we are going to cover this chapter. And here there is a principle which we call the principle of locality, which we need to understand in order to, when we are going to use the memory to read the or write the data. So I think we know that, guys, the memory categorization, like the memory which is close to the processor is called the, I think I should start from here to understand this, explain this point. The memory which is close to the CPU is basically the cache memory. Cache memory. Okay, so this is what we have, and cache have two levels, level 1 and level 2, which is near to the CPU. Okay, and as this pyramid is showing, the size of this memory is less compared to the other memory as we go down. Like the main memory is here, then we go to the secondary memory, the more size here. But as we going down, the size is increasing, guys, but the speed of the operation is also slower here. Okay, as we go up, the memory is very fast, more access, access time is very less. Access time is very less, so it means it is very fast memory over there. So the point is that if you want to store large amount of data, we cannot store in the cache. So what do we need? We need to store that one in the secondary memory, large amount of data. The thing is that how CPU can access this information from this, whenever he needed. So processor just check first thing, okay, whether it is available in the cache or not. Okay, if it is available in the cache, this process is called the hit. Yani processor looking for a data, and with that data is available here in the cache, so it is called the hit. For example, if data is not here, so we call that one as a miss. So when there is a miss, CPU need to spend more time to go down and search the data, whether it is available in the main memory, main yani RAM memory. If it is there, it's fine. Search it and then bring it into the cache, then supply to the CPU. So there is, miss penalty. What we call the miss penalty is basically the time required to go to the lower level and bring the data to the upper level of the memory. This is called basically miss penalty. So hope what is hit, what is miss, it is clear to you, right? Other thing is that suppose if it's not in the main memory, then you need to search to the secondary memory also. The same thing is that. So this is the way how this memory can be accessed, data can be accessed from the memory by the CPU. This is something. Also, a few information is mentioned here. The word is the number of bits a processor can process. For example, the CPU, this one MIPS architecture, which we learn in the previous chapter, we discuss everything. It is 32-bit, microprocessor. 32-bit means the word size is 32-bit. It means is that means a data of 32-bit long can be processed, can be added, subtract, multiply, and we can process 32-bit data. It is the word length is 32-bit. Similarly, we can have 64-bit, we can have 8-bit, and like that. So what we are storing here in the cache, because the size is very small, so usually 4 to 8 bytes or words we can store there. This is level 2 cache. For simplicity, better you just think as a 3 categorization: cache memory, then main memory, and the secondary memory. Cache have 2 levels, level 1 and level 2. So here level 2 we can have more information stored, which is like how much we can store. We can store 8 to 32 bytes, and what we called the block here. This much of bytes are called block, and 4 to 8 bytes we call that one as a word. And then we go to the secondary memory, which is, we know that the large amount of data can be stored there. So it is like disk, we called as a pages there, because there are disk sectors, and this is called as a pages. So this is what how the memory hierarchy is is there with this pyramid, we can understand. Now, coming to the concept of the first slide, what was that? The principle of locality. So now I think it will be clear to you what is the principle of locality. So programs access a small portion of their address space at any time. So addresses can be accessed at any time. So there are two ways to access the address. First is the temporal locality. Another one is spatial locality. So temporal locality is also called as the locality in time, and spatial locality called as locality in space. Okay. So temporal locality means the items accessed recently, yani the address or items which are accessing by the processor recently are likely to be accessed again. Okay. It means this is called the principle of locality. For example, instructions within a loop, which is just used or accessed because we know that the nature of the loop, it is going to be going to be repeat, so most likely it is going to be accessed again. This is something. Or induction variables, also an example of the temporal locality. Another kind of locality is called the spatial locality. What is that? Locality in space. What it says basically, it says that item contiguous near those accessed recently are likely to be accessed soon. Yani the items which are nearby, if you are accessing any item out of that, so nearby item will also going to be accessed, soon. It's like that. So like that, first example, you can understand like the code, which is sequential code. There is no like branch instruction something. It is just a sequential code need to access one instruction, then second instruction, third instruction. So need to read the word first address, second address, and so on. So sequential instructions like access, it's basically the principle of locality. Locality in space means we are accessing one address, then next we are going to access, then next we need to access. This is what is spatial locality. As well as the array data. So we know that whenever we access a data or element of a array, so we are not just only going to access one element. We may need to access more elements. So when we are doing like that, so it means we are taking advantage of the spatial locality. This is like that. So you will understand these things with an example. So I'll give you an example of it. You can think this piece of code. In this code, you can see there are two loops, upper and inner, and there are some variables. When this code is going to be execute, some variables are going to execute again and again. Can you just identify them? What are the variables which are going to access repeatedly? I exactly, J exactly, you are right. I, J, as well as itself we are accessing AI, right? Array also we are accessing. So these are what basically, because we just access it and we are going to access again. It means is that, what is that? This is time is this is a locality in time. The first one we are talking about. So this is the example, yani temporal locality, references to these things. Also, the another one is called spatial locality, and I told you about the spatial locality is that any item, the nearby address are going to be accessed soon. So here is the spatial locality, which is the array. And if you look in this array, girls, you are not only reading one element. You are with the help of I, we are reading next, all elements of AI. So this is what spatial locality means. So references AI, J, and I are the using temporary locality, and AI itself using the spatial locality as well. So taking advantage of the memory hierarchy, we know that what is a memory hierarchy. I have already discussed this one. Then store everything on the disk. We know that a large amount of data is going to store in the hard disk. Copy recently accessed and nearby item from disk to the smaller DRAM. Yani those are you are accessing recently. You need to copy to the DRAM memory, what we call main memory. From the disk we need to bring it here. Now copy more recently accessed and nearby item from DRAM, yani from the memory, to the smaller memory, which is SRAM, yani this is cache we are talking about. So cache memory attached to the CPU. I already explained to you. The large amount of data is going to be stored in the disk, and from the disk which you are accessing, it's going to be come into the main memory. Then more recently or more accessible items comes to the cache, okay, so that processor can continue the execution without interruption. Now guys, what I just explained here, you will also understand this is a processor. Here we have the cache, then here we have a main memory. So guys, one term come here, block, or what we call a line. It means is that unit of copying. Block yani unit of copying. How much we are copying. So block could be one word. I hope it is clear. The word means the number of bits a processor can process. It could be byte, it could be 2 byte, 4 byte, like that. So block may be multiple words. I told you this thing. Now, if access data is presented in the upper level, I told you this. In upper level, this is called the upper level, which is cache. If access data is present here, I told you it is called as a hit. So if this is a hit, processor no need to go down and search the data because it is already available in the upper portion. So processor will continue its execution. So hit access satisfied by the upper level. And there is a hit ratio, what we call, and what is that one? Hits over how many times we access the memory. So here, for example, this processor is trying to access this cache 10 times. Okay, and out of 10 times, it finds that the data is present in the cache itself out of 5 times. So we will be saying 5 over 10 because 5 times it is a hit, and over 10 because we try to do this one. So it means the ratio of 0.5 is the ratio. Okay. And now guys, as I told you, 5 times you are getting here, but what about the remaining 5 times where you did not get the data? So if access data is absent, yani what we call that one? We call this one as a miss. So in this case, block copied from the lower level, yani go to lower level, look for that block which you are looking for, bring that block here in the upper, then from that upper, it is gonna be served to the processor. It's like that. So girls, in this process, completed, need to spend time, and that time is basically called the miss penalty. So whenever there is a miss, there is a penalty of time which need to be spent in order to bring the data from the lower level to the upper level and then supply to the processor. So similarly, we have a miss ratio. Miss ratio means number of misses over number of access, how many times we are accessing. Moreover, we can get the miss ratio. If you know the hit ratio, 1 minus hit ratio, you can get the miss ratio as well. So this is something, and if there is a miss, block copied from the lower level and then access data supplied from the upper level. This is the way. So is this clear about what is miss and what is a hit and how processor is accessing data from the memory? Any question up to now, guys?
Clear.
All right. Anyone? Is it clear? All right, good. So let's continue then. And now we are going to take real examples after this more information. This is about, just to let you know, when we are saying the cache is very small. Okay, the reason why it is small is that because the technology used to design the cache is SRAM, basis semiconductor memory, is very expensive. Very advanced memory and as well as very expensive. If you look the typical access time of the cache, you will see this one. You will shock 0.5 to 2.5 nanosecond. This is the response time to read and write the data from the cache. On the other hand, if you look the price, which is $500 to $10,000 for per GB, so expensive. Okay. Now, We look for the memory DRAM, which we call RAM also, right? And this one, if you look, the access time is more here, even 10 times more if you look here like that. But if you look the price is very cheaper compared to that one. 500, not only $10 to $20. Similarly, the flash memories, pen drives we use nowadays, see the access time, 5,000 to 50,000 nanosecond. But see the price is so cheap, only $1. Then we go to the hard disk or magnetic disk. See the access time, 5 million to 20 million nanosecond. But if you look the price, see the price is 1,000 more than, even 10,000 less than compared to that one, many times less than. It's like that, only $0.1 compared to that one. So there is always a trade-off when you are designing a computer system, because we cannot have this all like a cache memory. The reason is so expensive, we cannot design it like that. So we need some cache memory, we need some DRAM, then we need definitely for the some magnetic disk, so that we can store large amount of data, because on the other hand we have to store large amount of data. So if you look what is the ideal memory, so we can say yes, ideal memory is the one whose access time is near to the cache or SRAM, but the capacity is like the disk. It's like that. Okay, hope you understand the concepts. Why do we have less cache and why do we have magnetic disk more? So it's like that. Yes.
It means the cache is the faster one.
Exactly. The cache is the fastest one. The reason, because of the response time. Yani the speed of operation when you are accessing the information is 0.5 nanosecond, just 0.5. And you can quickly, rapidly, you can read it, you can write it. But if you compare the magnetic disk, see 5 million nanosecond is writing and reading time. Though it is again a nanosecond, it's very fast. But compared to that one is very slow if you just compare it, right? This is something.
Yes.
Okay. Okay. So this is memory technology we are talking about. So like when we design a computer system, we need to take care of the money and what speed you need and how much data we need to store and so on. So all these things, then there is a trade-off always. Then we have some cache, some RAM, then some disk and all these things. Okay. So this is about the cache basics. So we have a cache memory which is near to the processor. Everyone now get the idea. So the thing is, processor needs some information, some data. So it will go to the cache. It will find it first. So if it is there, that's good. If not, it is called miss. Go down and bring it up. So how do we know if a data present in the cache or not? This question comes. We saw now is go there, it check it. So how processor is going there, going to check there whether the data is present or not? First question comes. Second question comes, if it is there, okay, how do we find it? How can we find that data? So with the time, you will be getting the answer of these two questions. First, whether the data is there or not. If yes, how can we find it? Okay. So here, the concept of mapping, actually, mapping is a technique through which lower order memory, blocks are going to map into the cache memory. Okay, so that we can locate what data we are looking for and we can bring it from the lower memory. So look here, what is direct mapping scheme? Each memory block is mapped to exactly one block in the cache. As I said, each memory block, which memory? Main memory, RAM block is mapped to exactly one block in the cache. Okay, lot of lower level blocks must share a block in the cache, because cache have very limited block. We know that, but memory have more blocks. So there is a mapping scheme, many to one. So there is a one place in the cache, you go there and you can find the reference of many blocks in the lower memory. This is the concept actually, which is called mapping. So multiple blocks of the main memory is gonna be mapped to a particular block in the cache. So processor will check in that block whether it is there or not. If it is not there, so it is going to map to multiple places in the main memory. So it can replace from the multiple any one of them what is needed actually. So just you understand what is mapping first, just wait to understand complete idea. Then we have how do we find whether the address which we are looking, okay, or which address is going to map to which block in the cache, okay, which address of the main memory content is going to map to which particular block in the cache. So there is a formula for that which will give you the answer of question number 2. Yani how do we find it? So it is like that: block address, yani the address of the block address of the main memory. Then we will be using here modulo operator, the modulo operator. Then here the number of blocks in the cache. So according to that formula, we can map a particular address block of the lower memory, any main memory, to a particular block. So we can say cache, and this formula can be just written in the sense like, what is that? It is like cache index, like that. Cache index is equal to block address, any which block in the cache. It means is that cache index is equal to block address modulo, then we are using number of blocks in the cache. So this is something. Now girls, as I said, so multiple blocks can be mapped to a particular block in the cache. But girls, how would we know that whether the data which is available in the cache, it is the correct one or not? Because multiple address can be mapped there. So in order to check whether the given present data there, it is the same which we are looking for, or it is from different address. So for that we have one more field which is called the tag field. Okay, so have a tag field associated each cache block. So in each cache block we will be having a tag field that contains the address information. Okay, the upper portion of the address actually require to identify the block, okay, which is basically the answer of question number 1. Yani this is how do we know if the data item is present in the cache or not. So depend upon we can check the tag field. If tag field is this tag field, the stored tag field in the cache, matching with the upper portion of the address which we are looking, it means we will say that the data is present there. Okay, this is the way. Okay, this with the examples things will be clear. Maybe something is blur, you will be not getting exact idea. You will be getting idea with this example now. So as I said, the upper one is basically your cache, girls. This is the cache. This is your RAM. Okay, and as I said, in the RAM is having more data compared to the cache. So cache has a limited number of places, okay, to having data. So these are the cache blocks. We can say 1, 2, 3, 4, 5, 8 blocks are there, 8 places like that. But in the RAM, we are having 32 blocks. So as I said, multiple blocks can be mapped to a particular cache block, okay, or cache here. So like if you just focus to the blue, so this one, this address data, this address data, this address, out of these 4, anyone can be here. Anyone can be here. It's like that. Okay. So how we know whether it is going to be here or somewhere? So for that, the formula is here: block address, then modulo, then block in the caches. Okay, girls. So first of all, you need to understand how many blocks are there in the cache. If you look here, we have 8 blocks in the cache. 8 blocks. So how can we represent 8 block? By using binary, we need 3 bits to represent the cache index. What we call this is cache index. So we need 3 bits starting with 0, 0, 0, the ending with 1, 1, 1. So we are having 8 blocks there. And by the way, blocks are always in power of 2. We will be not having like 5 blocks, 6 blocks. They will be a power of 2, 4, 8, 16, 32, and so on. Now here we are having 32. So girls, in order to write the all block numbers, 32 block numbers, how many bits we need? How many bits we need to represent 32 blocks? So it's again, as I said, 2's power 5. Yeah, exactly. So these are the 5 number of bits. So if you look these address, you can just see these are the 5 bits long. Okay, this is like that. So very first address of the block will be all zeros, then 1, then 2, 3, 4, then this is 5, then it's like that. So now let's see how we are saying that this blue is gonna be mapped here. So you use this formula, girls, which is block in and cache index, yani cache index is equal to what is that? Block address. Okay, which block address we are looking for, girls? We are looking for this block address. Okay, what is that? 0 0 1 0 1 modulus. So modulus operator you know very well. Okay, and we need to write blocks in the cache. So how many blocks we are having in the cache?
8.
8, exactly. 8. Okay, girls, can I write this 8 as a power of 2? Power of 2
to the power of 3.
2 to the power of 3, exactly. 2 to the power of 3. Okay, girls, here this is the beauty of the modulus operator, that if these 3 bits basically will tell you the result of it. It means is that any lower 3 bits are going to tell you which particular block of the cache this address is gonna be mapped, yani which is 101. If you just look the blue address, can you check it? It is 101 or not? This one 101, right? Yeah, so it is like mapping here, right? Similarly, girls, if you just try to find where it is gonna be map, what is that one? 0 1 1 0 1 modulus 2's power 3. As I said, again lower 3 bits just we need to focus. Again, it is gonna be same map to the same index or not in the cache?
Yes.
Okay, similarly, what is next one? If you just focus this one, next one, which is 1 0 1 1 0, no, one extra I just put here, 1 1 0 1. If you get it again modulus of it, you will again see, yes, same it is gonna be there, right? So it is also going to be there. Similarly, one more left, which is like that. If you check it, so it is gonna be again mapped. So it means is that out of these, either this or this, any address can be mapped to this index, which is 101. Okay, so processor will check in the here in the cache, and it found okay, data is available there. But girls, whether this data is the exact this address is the exact address from which we want to read the data, because it could be either this, it could be either this, it could be either this, it could be either this. So how we are going to differentiate these 4 address data there? So in order to differentiate that one, girls, remaining these 5 bits are called the index bits, 3 bits sorry, are called the index bits. The remaining bits, these 2, just focus here, 0 0 0 1 1 0 1 1. These bits are called tag bits. What they called? Tag bits. So we are not just going to store the data in the cache, we are also going to store here in the cache these tag bits, so that whenever processor need to read the data from some particular address like that, this one, so it will check first, okay, index is there, all right, it is there, found, very good, data is there. Now it will check whether is this the correct data, so it will also match this tag field. So if the tag field is matching with this field, we'll say okay, this is the exact data, but this is yani what we called hit. For example, if the processor is looking for 101, the tag which is stored here is 11. Tag stored there is 1 1. It means this is not matching. Are you getting my point?
Yes.
It is not
Yes.
matching. So when not matching, what we call this one? Miss. Getting? It is called a miss. It is not a hit. It is miss. And if this is a miss, what we need to do? So processor will spend some time. Processor will go to the lower memory. It will go to the lower memory here. It will check, okay, this is the exact data, and that data is gonna become here now. Okay, it will take some time, and then from here to here, it will send to the processor. This is the way basically how it works. So hope you got the idea, yani how the memory blocks are going to map to the cache by the using formula, and what are the index bits. As I said, these 3 bits are called the index bits of the address, and remaining 2 bits of the address are called the tag bits. So we are not just only going to store the data from these addresses here, we are also storing the tag here, so that processor will come and check data is valid, present. Okay, present. Now verify it. In order to verify, it will check the tag is matching. If yes, then it is called hit. If it is not matching, then it means bring the actual data out of 4 in the cache. This is something what's going to be there. So idea is clear to all of you?
Yeah, but I have a question.
Yes.
When is it possible to have a miss? I don't know how to explain it, but the memory location can't be removed and go anywhere else. So maybe the data is erased or something. I'm not sure how is it gonna be.
It's gonna be overwrite data. It is gonna be
Okay.
overwrite, because this is the cache, it has limited place space to have something. So in memory, always it is called the overwrite. So whatever is the current data which is not required, so what will do? It will be replaced by the next data. It is
Uh-huh.
it is gonna be overwrite. It is like that. This is the way. I will be discussing examples with the miss and what will happen with the miss and all. Just wait, inshallah. It will be more clear. So with the slides, inshallah, concepts going to be clear. So what we learn now, we learn that there are some index bits which we can get from this formula, which will tell us which particular block of the main memory going to map to which particular block in the cache. One thing. The remaining bits are called the tag bits, because we need to identify out of these 4 which one is the address which processor is looking for. So to differentiate these 4 blocks, we need to store the tag bits also. This is something. Now, so one more example here, the tag field. It's more about the tag field, though I already explained. How do we know which particular block is stored in the cache location? So you store block address as well as the data. So we will be storing data as well as the block address. Bus girls, why should we store complete address? Like, the address is 5-bit long here, 5-bit. So we don't need to store 5-bit. We need to just store only the tag, because actually only need higher order bits of the address, which we call the tag. As I told you, the 2 bits, remaining 2 bits are called the tag bits, which we are going to store in the cache along with the data. What if there is no data location, and there is nothing over there? So we have here valid bits. This valid bit basically tells whether some data is present or not. If it is 1, any data is present. If it is 0, it means there is no data present. It means like that. Initially, girls, when we turn on the computer system, we know that these memories which we are discussing, it is volatile. Then initially there is nothing. So valid bit is in the beginning, it is always 0, because there is no data in the cache, because you just turn on the PC. When you just turn on, there is nothing. But as the time passes, quickly, there will be some misses in the beginning that we call the cold misses. We will be discussing later on. Then later on, processor start fetching the data from the lower to upper. Then once it is, good large population of the data in the cache, so they start, hitting there, because data will be start presenting in that place. So one more example with the colored, yani it is the same but more detailed like that. This is the cache. This time we are having only 4 block in the cache. 4 block, you know that 2's power 2, yani we need 2 bits to have the index field. So like 00, 01, 10, 11. And then we have a valid bit. Valid bit will tell you whether data is there or not. As I said in the beginning, valid bit will be all 0. I mean, there is no data. Okay. Tag bits are what which is there. So just if you consider that in the very first thing and in the beginning, so valid bit is like 0, 0, 0. And processor want, to access some data from this address. Let's suppose from this address, processor need to access the data. Okay. And by the way, because as I told you, where it is gonna be any index is equal to address which we are looking. So how these gonna be mapped there, you can just take any these 2 bits. So 1 0 0, sorry, all are zeros. Then modulo, we need 2's power 2 because there are only 4 blocks here. So it means we need only just 2 bits to identify which particular block this address is going to be mapped. So we can see now these 2 bits, which is red, is telling you which particular cache block it is going to be mapped. Like the red one is going to be mapped here, which is 0 0. And see the another red one is here. And when you read the first one, it's like that. Okay, it's like that. It's going to be mapped. What about the remaining bits, girls? What we call these bits? Remaining 2 bits?
Tag.
Yeah, exactly. These are called the tag bits. Exactly. So for example, processor need to read data from this address. Try to understand my question. Okay. So PC program counter is having this address and need to read something. So it will go first in the cache. Okay. So as I said in the beginning, all valid bits are like 0 0 0. So processor first check whether there is a data, yani valid bit is there. So we'll see, okay, valid bits all are 0. It means it is miss or not. Because valid bit is telling you what it's telling, just read it. A field in the tables of the memory hierarchy that indicates that the associated block in the hierarchy contains valid data. So there is no data. Okay, it means this is the miss. When it is miss, processor will go down. But again, processor knows that by using these 2 bits, it can identify the particular block. So yani this is the index where we have to look. So here we check. Okay, valid bit is 0. There is no tag bit. Yani it is surely a miss. If this is a miss, go to the lower address now. And where to go? But when you go down, then again you will go to the 1 1. So 1 1 1 1. Where is the 1 1? Here is the 1 1. See, this is the 1 1. It could be this one. It could be this one, and it could be this one, and it could be this one. But what is that tag upper bits of this one? 0 1. Getting the point? 0 1. So out of this one, which one is needed? This one or not?
Yes.
Exactly. So from here, data will be coming here, as well as what will be the tag field? Tag field will be 0 1. Once data reach here, this valid bit will become now 1 because now it is a valid data. So this is miss penalty. Whenever there is a miss, go down and bring data here. Now, after that, data is available, and this is this way, it start accumulating data in the cache. This is the way basically how it works. Just wait, we have one more example for it in the next slide in more detail, so it will be clear. So what is valid bit? Hope it is clear. And what is whether the data is there. So compare the cache tag to the higher order 2 memory address bits to tell the memory block is in the cache or not. As I said, as I just tell you, this one is gonna be matched with that one. Okay, if it is there, then fine. If not, go down and bring it here. This is the way. Now consider some examples. So here, girls, in this example, we have given that there are 8 blocks in the cache, and each block is having one word. Yani per block only one word is there, one word. As I told you, each block, this is called the block, girls. You know that one block, two block, and how many we have? 8. Okay, and each one can store one word only here, because we can have here multiple, but what is given? Only one word. A word could be 1 byte long, 2 byte long, like that. Okay, so it's like that. So direct mapping scheme we are saying, and initial stage is there. So index of the blocks in the cache, valid bit all are no as 0, yani tag bit is empty, data is empty. This is the initial stage. Now we are going to reference some addresses, which, okay, so we are going to read the data from this address, which is basically decimal address. When we write it into binary, this is the address. Okay, girls. So from this address, processor will check there and go to the 110, and at that time it will check, because initially it was no. It means, is this miss or not? Because there was no data at that time. Okay, when there is a miss, what happened? What I told you, what need to do? Go down.
To the
memory. Data.
Exactly, go to main memory, and from there bring the data here. Okay, and where to bring? This is the cache block. And how do we know this is the cache block? Because of this 3 bits. So this way the data need to be there. So because we don't know what is that data, so what we are writing memory, go to memory and bring data from this address. So we are saying here is a data from the memory, from this address of the memory. So we are writing MEM 10110, yani memory, this address, whatever is data here, it is here, because we don't know what is the data. So we are writing address and that one. Or sometime we can also write this one like just in short, memory, and which address is this? Either I can mention like in decimal also 22, or I can write in as it is mentioned like that. It is like that. Okay, so this is the need to be there. So once it comes, it also, store the tag field, as I said. So remaining upper fields are bits are called the tag field. It is gonna also there. Once it's there, so valid bit will become now y, yani, or 1, yani it is now valid data there. It is like that. So it is a miss, but now after one miss, data is available here. Yani if this data is going to be used in future, this address is going to be accessed in future. So data is there already in the cache. So this way it will be hit at that time. Just wait now. Now, so this is the current situation of the cache. Let's suppose we are going to reference or read one more address. So again, 101. So where to look? You have to look 010. You go 010 and there was nothing at that time. So this is again a miss. When there is a miss, go down and bring the data to here and store the tag field also, which is this field. Okay, 11. So now data become valid and it is become 1, or yes and no we are using here. Okay, so 2 misses this way. Now guys, this time 22 and 26 we are going to read these address again. 22, when you go read, okay, 110, so you go 110. When you go 110, it means we are going to check here. Okay, we see here, yes, yani data is there. All right, now match the tag. Is this matching with the tag? We see 11010. It means is that yes, this is hit. What data we are looking, what address we are looking, exactly it is available there. So it is called the hit. So this time, no need to go to lower memory, no need to overwrite anything in the cache. Just it is called hit. This is like that. Now we are going to read the next address 26. So go and check 010. Okay, we go there 010. We found that okay, valid bit is 1, yani data is there, but whether it is the one we are looking for or not. So 1 match with this 1. Yes, this time also this data there. So read that data and supply to the processor directly. So it means is that after 2 miss, we are getting 2 hits now. Now we can have again more some references, like we are reading this time 16. Okay, because 000, and definitely in this cache block there was nothing. So if there is nothing, so yani go down and bring the data to this one and place the tag field, and definitely it is a miss as there was no data. Okay, 3001. So 001 is this one. Again, there is no data. So it is what we called, this is a miss. So the data will be there, and then it is like, now you are again accessing address number 16. So this time, if you go there, you will see that the same tag is already there and the data is already there. So it is gonna be hit this time. Okay, this is basically hit this time. So this is the, in the beginning there are some hit misses, but later on it is start misses, as you know we are having more data in the cache. Now again we are accessing 18010. 010 girls. If you remember 010, previously there was a different tag at there. You want to see? This is the third row. You go back, third row. Can you check it now? What was that? 11, right? 11. But because 11 was for previously stored. Now when we are accessing this one, so it's gonna be replaced with that one, because this block, this particular block, which is this one, can map 4 different addresses. We know that. So which is there presently can be override by the another one as per the requirement, okay, of the processor, whatever is looking for. It's like that. So this is like overwriting here. The red one is saying overwriting is here. So this is one example, girls, which I discussed. Now one more example to clear your concepts. So this time we are having cache, but there are 4 blocks only. How many blocks? 4 blocks. Each block can have one word. And girls, if you just look here, which type of locality advantage we get it here? Temporal locality or time locality? Time locality says the item you just recently accessed, you will be accessing again. So if you just look this example, so we check it here 16 and we bring this data here, 16 data, which is here now, here. Then after some time we are accessing is again. So the data is already there and we are making use of this one again. So which locality advantage we are using here? Is this time locality or not? Exactly, Mashal. It is a time locality because we recently access it, and in the future we are again accessing it recently. And this one is accessed here, then we are accessing again, and this time the data is already there. Okay. Here, girls, I also gave one example to the other groups. It is like you can consider, like you are sitting in the library, you went there to study computer organization course. Okay, then you find a table, then you sit there. All right, so you have your notebook with you. Now you are just reading the notes. Then you find, okay, in order to understand this course, I need the textbook. Okay, then you stand up because it's not on your table. If it is not on your table, it is like it is a miss. Okay, then you go there to the shelf, you find where are computer science, okay, here, then where is the CO, then you find, okay, this is the CO. Then you check that book, okay, and then after checking that concept which you are looking for, you check it and you just leave it there and you come back again. Okay, then again, after some time you need it again, book reference, that book, you will go again and check it and come back again. So you are wasting your time. What if in the one time when you go there to check the textbook, you bring that book and keep on your table, because as long as you are studying that particular course there, maybe you need it multiple times. So you bring that book and keep on the table, right? And you are now just check it, then you start working on it. And again, after some time you need it again. So you don't need to waste your time to go to the shelf and bring it here. So this is what we call temporal locality, because you recently access and now you are accessing again. So rather than wasting your time to go and fetch the data to the processor from the memory again and again, we just bring it on the table. Table yani on the cache, inside the cache, so that we can frequently access the data. Do you get this point? Okay, what we call this one? Time locality. Okay, another one is called space locality. space locality. I will be giving you example of the space locality. Let's just understand the example with this same library concept. So once you go and find the textbook of the CO girls, you find that in that continuation, when that CO textbook is there, the next and next books are also CO books. They are very good books and they are the reference book. Okay, because your table size is not going to have only one book. We can have multiple books now. You on your table in the cache there is a more places, yani not one word, we can have multiple words. So rather than just bringing one book, because you have the option to put two books on your table, so what you will do, you will also bring the next book which is near to your book, and you bring both of them and just keep on your table or put in your cache, with two words there. So whenever you need that one also, you can also access that one. That is called the space locality. Okay, we will be looking at the example with the multiple words per block. When it is there, then you will understand that concept. So for now, what is given to you? It is given that we are having 4 blocks and each block is having one word. Okay, one word only. So look now. So these are the addresses. I'm writing. This is written this time in the decimal numbers. We are going to access this one. So girls, we know that the maximum number here is 15. Maximum address is 15. And at least I need, how many bits I need to represent this address? 15? In
4.
binary? 4, exactly. So for your reference, I'm just writing here so that you can understand at least now. So 0 to 15, I am writing all, and all numbers is written in the 4 bits. So girls, do you remember the formula? Index, how do we find the index? Which is basically the block address, okay, modulo the number of blocks in the cache. So how many blocks we are having in the cache? 4, exactly. So 2's power 4, yani 2 bits. So lower 2 bits are the index bits to identify which particular block these addresses are gonna be mapped. Are you getting?
Yes.
Okay, this is like that. All right. So now girls, when I say 0, yani first address, I am going to access this one. Okay, this time we are not showing the valid what you call valid field. We are just showing a tag and this one data field. Okay, so when you are accessing 0, and how do you write 0? This is like that. And modulo 4, yani 0 0. It means we need to check here data. Okay, so is this available here? Data is available? Yes or no? Simple.
No, it's a miss.
No. So this is a miss. Exactly. This is a miss. When this is a miss, what we need to do? Go down to the lower memory and bring that data here. So we will be writing here memory 0. Yani bring the data. And girls, what are the tag bits? Can you just check it? 0 0. Getting? Yes, exactly. This one. All right. Now this is one. Now we are going to reference the second address, which is given here, which is 1. And for the 1, where it is gonna be mapped, you can check index 0 1. Index 0 1. So by the way, this whatever is the status, it is gonna be maintained, which is I am writing exactly. Now this is again a miss. Am I right? This is again a miss. If it is a miss, at that we need to bring this data from this address. And what will be the tag field? You can check it easily. The tag field is again
0 0.
Exactly, 0 0. Now we are reading this address 2. Okay, when you are reading 2, please check where it is gonna be, which index is gonna be mapped. It is going to map 1 0. When we are talking about 1 0, so this is the current status of the cache, which will be same. So I'm just copying this one so that this is the same thing. So when we go there, we find that there is nothing again. So it is also a miss. This time we need to read that at this one. And what is the tag field? It is again 0 0. Okay. Now before accessing the address 3rd, I'm just copying the current status of the cache. So this way we are having these data along with the tag fields. These are the addresses. Now 3 is also not there, girls. And by the way, where it is gonna be mapped? 3, any last one here. Okay, so this is also a miss. So we got now 4 miss. After 4 misses, now look what is the current status. This is the current status. Again, I am copying this one, the current status. Now, guys, what we are going to do? We are going to read this address number 4. Now, is this miss or not? This is also miss because 4, we need to check 0, 0. We go to 0, 0 and we try to match with that tag. Is this matching with that tag? This address?
No.
No, it means the data which is there is not the valid data. It is not the one which we are looking for. So what processor is going to do now? Processor is going to override this one. Getting the point? And in place of that, what we will be having? M4. Because this is the place where 0, 4, 8 will be there. And 12 will also be there. Getting how I'm saying these things? These things I am saying because of, if you just look the 0, 0. This is the 0, 0. This is the 0, 0. This is 0, 0. This is 0, 0. Yani 0, 4, 8, 12 can be mapped to the first location. That's why. So what is the tag field for this 4 girls? Tag field is 0, 1 and it is now 4. Getting point? And this is 0, 0 and this is the remaining is same. There is no change. The first entry is just basically override. So this is current status. Now we are reading address number 3. When we are reading address number 3, girls, you know that it is already present here. Am I right? So what is that now?
Hit.
Yes, it is a hit. So when there is a hit, no need to overwrite, no need to change anything. Same status is gonna be continue. Getting the point? It is same status will be there. The same status, same status. So again, you are reading 4. So 4 is there or not already? Correct?
Yes.
So one more hit. We got one more hit. Now 15. For the 15, which index is gonna be match? You look here, 1, 1, yani this last one. And what we have there already? 3. So this is miss or not? Yes, it is a miss. And what we will be having here now?
Memory 15.
Yeah. And then tag is gonna be 1, 1. And over there, it is same. There is no change. Like what was that? 1 earlier. And what was there? 2. So 0, 1, 0, 0. So this is the current status of the RAM after accessing or referencing these addresses. This is the last address here. So girls, how many times we access the memory? We access the 8 times. Out of 8 times, how many hits are there? 2 times. So what is the hit ratio if I ask you? What is the hit ratio? So it's very simple. Yeah, 2/8 is the hit ratio. If I ask you what is the miss ratio?
6/8.
6/8. That's it. So question may come like, okay, so you just access this thing and fill the information and show the what is the final status of the memory. So this is the final status of the cache. Okay, we can also ask how many hits are there, how many misses are there, like that. We put it in last because 3 is the index 1, 1 and 15 is the same. Yes, exactly. Yes, no. Because 15 yani index is 1, 1. That's why it is gonna be in 1, 1 because we know that this is the 1, 1. first thing. So, but when we check the tag which is stored earlier was 0, 0. But the tag of this 50 should be 1, 1. It means miss data is not the one which we are looking for. So then when it is going to be missed, so go down, bring the data from the 15, then replace with the 3 which was earlier there. It is like that. Very good. Okay, guys. So this is the way to understand. You need to complete it. Okay, this is the solution, complete solution.
Doctor, could we take a break?
Okay, let's take a break. No problem. So we'll start. We can have a break, then we can continue from here. No issues. Okay, guys. See this one. See this example.
Yeah.
So in this example, we have 4 blocks, and again each block can have 1 word. So, and if you look this one, 0 and 4, okay, they are going to refer one by one. So 0, what will be the index for 0? Because all are 0, 0, 0. So index will be 0 or not? Right? And what about the 4? Index is gonna be 0, 0 for it, because how do you write 4? 1, 0, 0. So last 2 bits, right? Last 2 bits. So it is gonna be also 4. It means is that either 0 or 4, both are going to be mapped to the same index, which is 0, 0. Did you get the point?
Yes.
Okay.
So it will be miss every time.
Exactly. It is gonna be miss every time, like this. It is gonna be miss every time. So first, because of 0, then because of we need to check to this location only. Okay, processor will check again, miss. Replacement is there. See, overwriting, but all times we are getting misses. Okay, this is called the ping pong effect. And 2 memories locations that map into the same cache block is basically here having this situation. Though we know that there is a lot of space in the cache, right? But we are not making use of, because of the mapping scheme is like that. These 2 addresses can be mapped to a single memory map, a single cache block. That's why this situation happening. So we will be, this is the issue. All the time we are getting all the misses. So let's consider another scenario where we are not going to take the just time locality advantage. We are going to take the space locality advantage as well. Yani, rather than just bringing one memory data to the cache, we will be bringing 2 consecutive addresses. Okay, and let's see that time how we will be getting advantage of it. So next question is about it. If you just check the heading, so 2 blocks, you can see 2 blocks this time, but 2 words per block. 2 blocks, 2 words per block. By the way, it is the same questions. This is the same question which we discussed earlier. Which one? The very first question, 0, 1, 2, 3, 4, 5. But we used to have that time 4 blocks. This time we have only 2 blocks. So saying 2 blocks, you can just easily understand how many bits we need, girls, for the indexing, because there are 2 index. There are 2 index, 0 and 1, right? But each is like that. Each one is having 2 words. Okay, so here we have to have word index. Yani which word I am talking about? Let's suppose this is word 0. This is what we call word 1. Then and so on like that. Okay, so word 0, yani first bit is saying it is about the word index, either 0 or 1. Second bit is telling it is for the index 0, right? Similarly, word 0 and 1, second bit is telling you it is referring to the index 1. Are you getting this point?
Can you repeat, doctor, please?
Okay, here I'm saying because now each block can have 2 words, right? So we know that how to find the this block index. But in this block, we have two words because of this is arranged like that. So which word we are looking for? We need to have word index also. So out of these bits, the first bit is basically telling you the word index, yani whether it is this word or this word. Getting now?
Yes, clear.
Second bit will tell you this index or this index, this block or this block, because two blocks are there. It's like that. So because of two blocks, we need only one bit. So we can just mention the address by using two bits, 00, 01, 10, 11. This is the way to write four words here. So now we are going to understand how it is going to be access the information. So first, address 0. Address 0. So is this miss or not? It is miss. Okay.
Yes.
And it is going to refer to the block 0, this one. So if this is a miss, we will be bringing memory 0 data here. But we will be not bringing only one word. If you remember what I said, the space locality, we will be not bringing only one book. We will also bring the book which is near to that one. So same way, we will be not bringing only one location. Here, we will be bringing next location as well. Are you getting?
Yes.
Okay. And what is the tag field for 0? Like this. Exactly. So this is the current situation now, which I am copying here. Current situation. Now you are accessing 1. Where you have to find 1, 0, 1, which is here. So is this miss or hit?
Hit.
Exactly. It is hit because of we are not only going to take advantage of the temporal locality or time locality, we are also getting the advantage of space locality. So we are also bringing one more content there. This is a hit. Exactly. Now you are accessing 2. So 2 yani 10, 10 yani this one, right? Exactly, Nora. This is a miss. If this is a miss, so same content will be there. I am just showing this one. And because of this miss, what we will be bringing here? 3. As well as what we will also bring? 4. And what is the index? 0, 0, right? This is the no, Nora, we'll be not bringing 2 because this is lower world. This is the next world. So if we are bringing here 3, so here we will be bringing. Oh, sorry. I am doing some mistake. Yes, it should be 2. So it is 2, right? So it will be 3. It's like that. All right, now correct. Now, girls, so this is the current situation of the cache I am just mentioning. Now tell me, when you are going to access address 3, what will happen? Yes, exactly, hit. Yes. Now this is the current situation, and in this current situation you are going to access 4 now. So is this? Yes, it is miss. Okay, but 4, where 4 is going to be written? Look, 0, 0, right? And 0, 0, what we have already? We have M0. So M0 is gonna be replaced with 4 in the top left, right? So when you bring 4, you will not only bring 4. What we will bring? Exactly, like that. And for the 4, what is the tag? If you look, the tag is 0, 1. And by the way, for the 5, the tag is also same. Keep in mind, okay? Like that. Now, so this is the current situation. You want now 3. So what will happen?
Hit.
Hit, exactly, because 3 is already present. So it is a hit. So this is the current situation with the hit. All right. Now, after hit, we need 4. This is that one. And M3, M2. And as you said, what about this when you read the 4, address 4? It is also a hit. Exactly. It is hit. Now, guys, this time 15, which is here 15, right? So for the 15, 1, 1. But if you look 1, 1, 1, 1 is this location, right? This location, if you remember like that, I told you. So this location, but it is already there. So what is gonna be now? It is gonna be override. Yani it will be now M15. Getting my point? And what is the tag field? 1, 1. So what is the lower address? Because lower address has to be here. You know that?
14.
Exactly. So we will be bringing here 14, not the 16. Keep in mind, because of the address. Rightmost is the lower, then the left is the like that. So upper is no change, by the way. So after this referencing, then you can see this is a basically miss. Okay, so this is the last status of the cache after referencing all these addresses, given address, right? Now, guys, if I ask you, can you check the hit ratio now? How many hits are there? 1, 2, 3, 4. 4 hits, because each block is containing 2 words and we are getting 4 hits. Do you remember how many hits was there when we were using one block?
2
One
hits.
word, 2 hits only. Yes, exactly. If you go back and check, that time only 2 hits. We got it. See, 2 hits. This one and this one, just 2. So this is the advantage of using the both temporal as well as spatial locality. So here we are getting more number of hits, any more good performance compared to that one. It is like that. Okay. Any question here? Clear to all of you? All right. So this is the current situation, right? This is the final situation. All right. 2 blocks per words. Now, guys. So here we have just whatever we discussed up till now, we discussed general. Now just discuss specific. The processor, what we discussed in our last chapters, the processor was 32-bit. Do you remember the number of address bits required there? Number of address bits of the 32-bit MIPS processor? How many address bits we use there?
5.
No, why 5? The 5 we use to read the registers. 5 bits to reference the 32 registers. But the memory, think about memory, dear. It's not register. We are not reading registers. We are reading memory now.
It's 31.
0 to 31. Yani 32. How can you forget? I told you address bus, data bus, all are 32-bit long. Okay. So 32-bit address now. So 30 out of these 32-bit address, how we are going to access the memory? Look here now. So here, this is the memory, girls. And in this memory, we have these indexes. How many indexes are there? 0 to 1024. How many totals? Including 0, 1024. Can I write like this? 2's power 10. Okay. So 10 basically are what? For index. This is your cache now, right? This is for the index. Okay. So look here how this 32-bit address is gonna be break now. Okay. Do you also remember the data size? Oh, sorry. Yes, out of this 32, what about the data? Data is also 32-bit long. Remember the data. So 32-bit long. How many bytes are there in 32-bit?
4 by
4 byte. Exactly. 4 bytes are there. So we are going to store here bytes as well. So word is like something word what we called. This is a complete word. We are saying like example word. But how many bytes are there? 4. You know that one 4, right? And do you remember the instructions? Can access any byte, store half, load half, read half. So we should also have management to read any one of the byte. So we should have the byte offset. Okay, we are going to store one word which is 32-bit long, but out of these 32-bit data, I'm talking about data now, right? Which we are storing in the cache. This data is basically having 4 bytes. We can read any particular byte or we can reference to any particular byte. So how many bits we need to reference these byte offset? 4 bytes are there. So bits required to reference these 4 bytes. How many it will be? Will it be 2?
32-bit.
No. I am saying we have 4 bytes, okay? And 4 bytes, this time, people get confused with that one. It's so simple. 4 bytes. I am saying 4 bytes, okay? So how can I identify which byte I am talking about out of these 4? So how many bits can tell me the index of these bytes? You think like that. So index 00, index 01, index 10, index 11. I'm talking about the index. How we will identify out of these 4 whom I am talking about. So we need 2 bits as a byte offset. Is it clear or not?
Yes.
Yes.
Okay, so look here. Out of 32, lower 2 bits are basically reserved for the byte offset. Yani, if I say here 00, yani I am talking about this byte. Is it clear now? Getting?
Yes.
All right. Then how many blocks we have in the cache? I told you 1024. Yani index bits for the block in the cache is basically 10. So 2 bits for the byte offset, 10 byte for the index. Now what is remaining? Out of 32, we have total 32-bit address. Out of these 32-bit address, 10 already removed for the block index. Then what is removed? Already 2 bits for the byte offset. So how many is remaining? 20 bits. And this is basically the tag bits. Getting? Which is here. So what we have? 20 tag bit, 10 offset bit, and 2 this one. So how many total bits now? 32?
Yes.
Okay, so this is the 32-bit address actually. Now it is broken into this steps basically. Okay, so now, so this is a cache. As I said, in the cache, how many bytes we are storing? So can I say each block can have 32-bit data? Okay, or one word we are saying now, word size. This is word. So I can say how many words will be there, girls? Can I say it will be 1024 words? Am I right?
Yes.
And do you know how many bytes in each word?
4.
Exactly. And 1024. And do you remember what we called 1024? Do we call as a kilo? 1024? Okay, so can we say now 4 kilobyte memory? This is here mentioned, this much of word or 4 kilobyte of memory. Yani this cache can hold 4 kilobyte of data. Is this clear, girls, now?
Yes.
Okay, so 4 kilobyte of data, yeah, 4 KB cache we will be having, and we can have this much of data. But girls, if you look this block, are we storing only the word here, or we are storing other information as well? If you look in each block, how many bits you are storing in actual? Are we storing the tag also or not, other than the word data?
Yes.
And 1 bit for the valid. So if I just ask you how much total in each column, so you will say, sir, 1 bit for the valid, 20 bit for the tag, and 32 bit for the data. Yani total what I am having here, 53 bits per block. Are you getting my point?
Yes.
And how many blocks are there? So this much of bits are storing there in this cache. Getting this point now?
Yes.
Yes.
Okay. One more information. I told you that here in the cache, we can store multiple words. Like in the previous example, I told you how many words was there? 2, right? But what we are considering here, only 1 word, which is 32-bit long. Clear, girls? So here are the formula, general formula. Now please have a look. So direct cache map we are talking. The cache size is 2's power n block, and n is the number of we use for the index, yani which is 10. We have discussed. The block size, girls, block size is 2's power m word. This is called block size. And block size, when we say 1 word per block, yani m is equal to 0. Getting the point? So this formula we use, what is the size of the block. So we consider that the 1 word per block we are storing, it means m is equal to 0. But girls, we also know that when I'm saying 2's power m word per block, and we also know that what are the words? Words, if we convert into the bytes, so I can say it is basically what? 4 bytes. Can we write the bytes like 2's power 2?
Yes.
So when you just simplify this one, can I write 2's power m plus 2 number of bytes? Right? It's like that. Okay, which is mentioned here, just to show you what is mentioned here. Okay, just explain the concept. So this way, girls, the tag field size you can get from this formula. 32 minus n plus m plus 2. By the way, we said word size is only, block size is 1 word, so m will be 0. So this is the way. But in some cases, the word size could be more. Okay, if this is more, definitely you have to put this value here. So this is one formula, general. Another formula, if you look here, girls, this is what the number of bits in such a cache is. Number of bits. This is about that calculation which I just explained to you. Okay, the number of bits. So how we will be knowing? First of all, how many blocks we are having? We have 2's power n. Then each block, what we are having? 2's power m words, and each word is 32-bit long. It's like that. Okay, so this formula comes actually for the number of bits. Okay, in each such type of the cache. So based on that, there is a question from the book. You can have a look on it. This is the question. So they are asking how many total bits are required to direct map scheme, which is 16 kilobyte of the data, and word 4 word per block. Assume 32-bit addressing. So girls, here first of all, when I am saying 16 kilobyte of data, it means is that how many words are there, because it is written in kilobyte. Can we convert it into words? In order to convert it into words, what I need to write? Divide by 4.
4.
So 4 words like that, huh? It will be like that. Just a minute. No, just a minute. How they are writing this one? Okay, 16 kilobyte. 16 kilobytes. Yani 16 kilobytes. It is gonna be. How can we write this one in terms of words? If you wanna write it, 16 multiplied by 1024. It's like that, right? And then we are converting into words. Okay, divided by 4. When we multiply, this will be 4. What we will be getting? 4096, which is basically 2's power 12 words. This much of the words will be there. Okay. Now, with block size of 4 word, yani in each block, we are having 4 words. It means is that this is 4 words, yani M size is 2. First of all, try to understand. And this is, we have 1024 blocks, yani n is equal to 10. Just put in the formula. This here, this and this one, and then you will be getting this much of total bytes will be there in the cache. This is one type of question. One more question come like that, which is, these are from the book itself. You can check. So they are asking this time, consider a cache of 64 blocks. How many? 64 blocks. Yani we are having like that, 64s. Okay, 64 blocks. Dot. So like block 0, block 1, block 2. How many we have? 64. Last is 63. And block size is 16 bytes. And each block we are having 16 bytes. So, yani, I am showing here 16 bytes. So byte 0, byte 1, and what will be the byte? 15 here. Then we will be having 16, 17, then we will be having 31 and so on. Then they are asking to whom block the number does address. Yani this is the address. Is gonna be mapped now. To which block number? Block number it is asking. Okay, so there is a formula. Block address, simple. Which block address? Because we have many blocks, 0 to 15 and so on, this one. So which block address it's talking about? So for that, first the byte address over the number of bytes per block. So byte address is given to you already, which is, this is the byte address over the number of bytes per block. How much? 16. So we get 75. So it will be somewhere here. Now they are asking which block, yani. So for block number, the block address. So yes, block address is clear to us. And then use the modulus operator. So 75 modulo this, you will be getting 11. So yani, this is the 11 block where this is gonna be located. They're just showing here 0 to 3. So 4 byte is using for the byte offset. Byte offset, because 16 is equal to 2's power 4. So 4 bits for the byte offset, 6 bits for the block, because this is 64. 64 yani 2's power 6. And remaining are the tag, which is 22. It should be 31. It's like that. Okay, this is what the address is. So clear this one, guys? Understand up to here?